Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 1.4 from your textbook, which was our initial discussion into how to solve different types of differential equations, starting with what we called separable differential equations. In this video, we're going to do just a couple more quick examples to sort of make sure that we're comfortable with this concept of solving separable differential equations. And then we're also going to have a few interesting sort of examples and a little bit of commentary just about solution sets to differential equations, because as we're sort of seeing, that's something that can get a little bit complex with the idea of a general solution, some particular solutions that might not fit the general solution, so on and so forth. So this video will be a little bit on the computational side at the beginning, and then we'll get into some just examples and thinking about the solution sets to different differential equations. So, first of all, we'll just start off with trying to find all the solutions to this differential equation, xy prime minus 1 over y cubed times the square root of 1 minus x squared equals 0 on the interval 0, 1. Whenever you see like interval 0, 1, that means x in 0 to 1. So the interval is always referencing the independent variable. And notice it makes sense that we'd be working on 0 to 1 because if you were outside of that interval of 0 to 1, that square root of 1 minus x squared would maybe begin to be undefined, so there could be some issues there. So we're working from 0 to 1 here. All right, so let's go ahead and take a look at this. We'll just rewrite the differential equations to start off with. So we've got our differential equation there equal to 0. All right, so our goal, of course, again, is that hopefully we can separate this. So we'd like to get it as a function of x and a function of y sort of separately. Let's first begin by sort of putting this onto the other side. So we get xy prime is 1 over y cubed square root 1 minus x squared. Then we could go ahead and divide by x to isolate the y prime there. So we get y prime is 1 over xy cubed square root 1 minus x squared. All right, a couple things to mention there. Of course, with that division, we'd have to assume that x is not equal to 0. There's actually two reasons why in this case we're not particularly concerned about that. One is in general, when we're solving differential equations, we don't really care about issues for the independent variable, again, because those are domain issues. But even more importantly, we actually have in this case that the interval is 0 to 1. And notice that that's a exclusive interval, so the 0 is not included in it, which means that we don't even need to be concerned that there's a potential that x is equal to 0, since we know we're on an interval where x is not equal to 0. So we're all good on just proceeding to this point here. All right, now, this is a little bit messy, but actually this is a good thing, right? For being a separable differential equation, having products or quotients are what we want. We don't really want additions and subtractions because those are separate terms and we'll be unable to sort of bring the y piece over. But in this case, everything's multiplied together, so as long as we multiply the y cubed onto the other side, we should be all good. So we have y cubed y prime is 1 over x root 1 minus x squared. Any concerns about multiplying y cubed over? Nope, only division would be something that we would be concerned about having like a divide by 0, but multiplication, not a concern there. So this is now separated, so we can go ahead and use our theorem that says we just need to integrate each side with respect to their respective variables. So we can integrate the left-hand side is the integral of y cubed dy, and we can integrate the right-hand side as the integral of 1 over x root 1 minus x squared dx. The left-hand side is not particularly bad to just go ahead and integrate. That's just 1/4 y to the 4th. The right-hand side is a little bit messier because we might be tempted to use like a u sub, like u equals 1 minus x squared, but unfortunately that x is in the denominator. If the x was up here, that would work nicely. So instead, we might actually end up needing to do something like trigonometric substitution. And again, trig sub is sort of hinted at here because we have a radical, and we have something that is either like an a squared minus x squared, an a squared plus x squared, or an x squared minus a squared inside the radical. Since we sort of don't want to break the flow of like generally solving this, what I would recommend if you guys were doing this, I don't think you need to hold, bring this along at each step of your integration. So you might as well just pull this off to the side, work on it, and then we can fill in here once we actually know what the antiderivative is. So we'll just grab this thing for right now, and we'll sort of go work over here on it. So we'll give ourselves, there seems to be just an erroneous little piece there. So we'll just work over here. We want to just integrate 1 over x root 1 minus x squared dx. So this is a trig sum. The correct substitution would be sine of theta because we have a 1 minus x squared. Remember, you got to also substitute for the operator, so that dx, the differential, that's going to be cosine theta d theta. So we can pop that stuff in there. We get 1 over sine theta, and then square root 1 minus sine squared theta, and then the dx, of course, it is going to become the cosine theta d theta. We can go a little bit further then. That's going to be 1 over sine theta. Of course, the whole point is that we get a Pythagorean identity here. 1 minus sine squared is cosine squared, so we get square root cosine squared theta, and then we have our cosine theta d theta. And hopefully we can take the next step sort of simultaneously. Square root of that square is just going to become cosine theta, and those cosine thetas are going to strike out. So we have 1 over sine theta d theta. We're not particularly thrilled to see a trigonometric function in the denominator because there's not a lot of good ways to integrate things that have a trigonometric function in the denominator. Luckily, though, we can just rewrite this as a different trigonometric function. This is, of course, the integral of cosecant theta d theta. And this is one of those ones that we have an antiderivative for. It's negative ln absolute value cosecant theta plus cotangent theta. Very similar to the integral of secant theta being ln secant theta plus tangent theta. This just has that negative n, negative ln, and also, of course, the co-functions. So, and of course, we know that we would get our plus c there. Of course, this wouldn't make a lot of sense to stick back over here because this is in a totally different variable. So let's go ahead and undo our substitution just as a quick review for that. Well, remember that x is equal to sine theta, or if you prefer, you can think about that as sine theta is equal to x. I'm going to admit that part of this example is just to make sure that you guys see some examples of all the different techniques of integration. So we're just doing a quick review here on trigonometric substitution. So if we draw ourselves a little triangle, we can label this part as theta, and we can label the triangle so that we have sine of this to be x. It might help to think about that as x over 1. As we know, sine is opposite over hypotenuse, so we can put a x here and a 1 there. Use Pythagorean identity to get that that is square root 1 minus x squared. And now we can just simply fill in what cosecant and cotangent is. Cosecant of an angle is the hypotenuse over the opposite. So we know that cosecant theta is actually going to be 1 over x. Did I really need this fancy triangle for cosecant? Of course not. If x is sine theta, then 1 over x is 1 over sine, which is going to be that cosecant. But we definitely need it for the cotangent part. Tangent is opposite over adjacent, so cotangent is going to be that adjacent over the opposite. So we get that square root 1 minus x squared over x. So we can go ahead and throw this stuff into here and replace it all the way back over there. Notice that this is definitely worth doing separately because you wouldn't want to have to do all that and keep this along the entire time. So we now have over here that we should have the negative ln absolute value. Our cosecant is 1 over x, and then plus the cotangent, which we found to be square root 1 minus x squared over x. Close up that absolute value and put our plus c. All right, couple little manipulations. What can we notice here? Well, we can make use of our interval that we're on 0 to 1 and recognize that it is completely pointless to have absolute value bars since we know x is going to be between 0 and 1. All this stuff is going to be positive. So if we wanted to be a little bit fancier, we could rewrite this just as negative ln of 1 over x plus square root 1 minus x squared over x plus c. Do we want to solve explicitly for y? Not really. I mean, we could go ahead and multiply both sides by 4. That would be totally fine. We could get this as y to the 4th is negative 4 ln 1 over x plus square root 1 minus x squared over x. And of course, when we multiply that plus c by 4, we get plus 4c, which is just a new constant. So we can just say plus c. But at this point, you would probably want to stop because if you went ahead and applied the fourth root to both sides, you would have to use plus or minus. You might say, well, can't we just assume that we have a positive root? Well, we don't have any information about where y is located. We just know x is between 0 and 1. But of course, we could have positive or negative values of y. So in general, if you run into sort of a not completely invertible function, right, the 1/4 root is sort of a semi-inverse, I would definitely avoid going any further. So this is a totally appropriate sort of place to end here, even though it's still in an implicit format. So there we go. There's another example of running through and doing a separable differential equation. A couple new things in this is that it was much messier to actually do the integration, just as a review to make sure you guys are still good with trigonometric substitution. Also, this was an example of one that was on a limited interval just because of some of the things in there. Of course, that didn't really have a big impact except to make things actually a little easier, right? Because we were able to like drop those absolute value bars. Also, this is just a reminder that there's going to be plenty of times where we're trying to solve something and putting it into an explicit format is just going to be too much work. It's totally fine to leave things as an implicit format. Unless the question, I guess, explicitly says it must be in an explicit format. All right, let's go ahead and take a look at another example then. All right, so this is probably going to be pretty much our last, for at least in this section, just directly an example of doing a separable differential equation. And the reason I want to do this one is because, as we'll see sort of at the beginning, this is a format that does not look particularly good for being separable. So let's launch into trying to do this. Notice there's no domain restrictions on this guy, so we'll just proceed forward, which is usually the direction you want to move. So we can go ahead and just start by rewriting this. Okay. Let's begin by getting this stuff onto the other side. We can isolate that y prime. If you think something is separable, that's going to be your first step. So you want to isolate the y prime. And then at this point, you're not particularly thrilled. Because remember that to get something into a separable format, you sort of want it where you have a function of x and that function of y, and then you can divide the function of y over. When you see several terms, things separated by additions and subtractions, that is not a good sign for being separable, because how are we going to bring the y terms over, right? We can't bring them over because one of them is mixed with x and we have another one that's just by itself completely. Well, the sort of trick here, though, is that separable is good with multiplications and divisions, so multiplications and quotients. So maybe we can attempt to try to factor this and actually separate that way. So let's see what happens if we try to factor this. We can try to maybe do like a factoring by grouping, and we can recognize we can take like a 3 out of the first part, x squared plus 1, and we can actually take a minus y out of the second part and get x squared plus 1. And then we can factor that x squared plus 1 out front, and we can get x squared plus 1 and 3 minus y. Now this is great for being separable because there's our function of x, there's our function of y. All we need to do now is divide this over. So let's go ahead and do that. We get 1 over 3 minus y prime is equal to x squared plus 1. Now, dividing over by a function of the dependent variable, a little bit risky, so we'll just have to make our note here that this is not equal to 0. Okay, we could go check that right now if we wanted to, or we can save it for later. It's up to you guys, but we got to make sure we come back and look at that at some point. So we'll just go ahead, put that in sort of red there so that we know that we come back to it. Okay, at this point though, this is separated. This is the function of y over here. This is the function x over here. So we can go ahead and integrate both sides with respect to their respective variables. So 1 over 3 minus y dy and the integral of x squared plus 1 dx. Remember, we proved that theorem in the last video that allows us to take that step. All right, over here, we could do u substitution, but hopefully we can see what's going to happen here. The derivative here is -1, so we're just going to get an extra negative sign. And we're going to negative ln absolute value 3 minus y. And then over on the right-hand side here, just a direct integral, 1/3 x cubed plus x plus c there. All right, so there we go. That doesn't look too bad. Now we can do a little bit of manipulation. I guess we could bring that -1 over onto the other side. So ln absolute value 3 minus y, -1/3 x cubed minus x. But of course here we would get -c, but that's still just a constant, so we can call it plus c. All right, we can use that trick to unpack the logarithm there. So we can say that the absolute value of 3 minus 1 is e to the negative 1/3 x cubed minus x plus c. We can take this e plus c and think about that as absolute value 3 minus y equals e to the negative 1/3 x cubed minus x times e to the c. Whole point of doing that, and again, as you guys do this more, you can make the jump from here to the next step in one go. But this, of course, is now another constant, so we can just put a constant in front. Absolute value 3 minus y equals c e to the minus 1/3 x cubed minus x. And then, of course, as we mentioned, and if you read through your textbook, you saw that explanation in there. If you choose the appropriate choice of constant, you don't have to worry about that absolute value. So we can say 3 minus y is c e to the minus 1/3 x cubed minus x. So this time it looks like we could easily go ahead and get an explicit form for this. Looks like we should be able to get this as minus y is c e to the minus 1/3 x cubed minus x minus 3. And then if we negate both sides, we could get y equals 3. And then, of course, we could say minus c e to the negative 1/3 x cubed minus x. But minus c, that's the same as just another constant. So we could say plus c e to the minus 1/3 x cubed minus x. Would it be wrong to write your answer as y equals 3 minus c e to the minus 1/3 x cubed minus x? Absolutely not, because that's still just saying the same constant, right? It's just that my constant here, the plus c, would be the negative of that negative c constant. Again, it's just an arbitrary constant, so it's totally fine to write it either way. All right, so there we go. Is that containing all of our solutions? Well, we don't know. We got to go back up here and think about this thing here. So let's see if this even is a solution. So we need to check this. So let's go ahead and check 3 minus y equals 0, which is the same as y equals 3. Now you can check this into any form of the differential equation before your division, right? So as long as it's before you did that thing that caused you to write this down, you can use that. So you can check this back in here, or if you want to make it easier on yourself, you can check it back in here. If y equals 3, then that left-hand side, y prime is going to be 0, because the derivative of a constant is 0. And on the right-hand side, if you plug in y equals 3, you get x squared plus 1 times 3 minus 3, which is times 0. So you would get 0. So this works. So y equals 3 is a solution. Okay, so we got to include y equals 3. So we come back over here, and we start to write y equals 3. But it's actually not necessary, because notice that if you use this piece here and you let c equal 0, well, then this would drop out and you would get y equals 3. So that y equals 3 is included. So that y equals 3, that extra solution that we found, is actually included in this. So our solution set is actually just what we originally found, y equals 3 plus c e to the minus 1/3 x cubed minus x, which means that this is the general solution. How do we know it's the general solution? Well, all of the solutions, everything like this, and of course this guy here, can be written in this format. So this is actually a general solution in this case. So we actually found the general solution for this. All right, so that tells us, right, that in this case, right, a little bit messy with some of the algebraic operations, but in terms of the integration, nice and straightforward. Main point of this example is just to show you that in this format, things did not look particularly hopeful for being separable, but by factoring, we were able to find the two functions, the function of x and the function of y. Remember, you have to be able to get a function entirely of x and a function only of y to be able to use this separable technique. All right. Now I want to get into some more interesting, sort of bizarre examples of working with these solution sets and understanding exactly sort of all the theory that's sort of going on behind this. So I'd like to turn attention to a very sort of interesting IVP question, and it'll also give us a little bit of practice back from some of the earlier things involving the existence and uniqueness theorem. So we're going to go ahead and consider this differential equation. We've got y prime equals e to the x squared arctan of y, y squared. we're going to do two things with this. We're going to prove that every IVP to this differential equation has a unique solution, and then we're going to find the unique solution to the IVP with the initial condition y of 0 equals 0. So let's start with A. We've got a couple different ways of proving that every IVP has a unique solution. Those are the existence and uniqueness theorems. Remember, we've got an existence and uniqueness theorem for linear differential equations. This guy, definitely not linear. You've got arctan of y, you've got y squared. Those are functions of the dependent variable, definitely not linear. We also have an existence and uniqueness theorem, though, for first orders. And this is first order, so we can try that. So we're going to try the existence and uniqueness theorem for first order diffees. So this is already in the format y prime equals a function of x and y. It's this messy e to the x squared arctan y squared. So that tells us that f of xy, and the notation of that theorem is e to the x squared arctan y squared. And the partial of f with respect to y, which is the other thing we need to check, well, it's going to be a product rule based on this, ignoring this guy as a constant because we're doing the partial with respect to y. So it looks like we get like e to the x squared, 1 over 1 plus y squared times y squared, plus e to the x squared, arctan of y times 2y. Now, these are pretty messy expressions, but arctangent, exponentials, squares, this, well, that's rational. We got to be a little bit worried, but you notice that this will never be 0 in the denominator. So there are no issues for discontinuities. So we can see that f of xy and the partial of f with respect to y are both continuous everywhere. So that tells us every IVP will have unique solution. So it is absolutely the case here that since the function and the partial with respect to y are both continuous everywhere, every IVP is going to have a unique solution. We're all good with that. So even though these are messy, there's no issues with discontinuity, especially since the only thing that sort of might have scared us right here with a denominator with 1 plus y squared, well, since this is 1 plus y squared, it can never be 0, so no issues there. All right. So now we're going to try to solve the IVP, y prime equals e to the x squared, arctangent of y times y squared, and we have y of 0 equals 0. So we have a little bit of information before we launch into this. We know that there is a unique solution to this. So there's only one function that satisfies this differential equation and has the initial condition that at x equals 0, y is also 0. Okay, this, while messy, is in a pretty nice separable format. Let's try to pull the arctangent or the y squared over. We can do those sort of simultaneously. So we can bring this over as 1 over y squared arctangent of y prime is equal to e to the x squared. Now, of course, when we did that, we have to make some notes here. That means that we're assuming y squared not equal to 0 and arctangent of y not equal to 0. Okay, at the next point, what we would need to do is we would need to integrate each side. Now, we're not going to actually do that because you guys should be very suspicious about trying to do that. On this side, this looks pretty horrendous because we have an arctangent in the denominator along with a y squared. And actually, on the right-hand side, we should be even more worried because actually, and we know that e to the x squared, while an integrable function, because it's continuous, does not have a closed form for its integral. So if the next thing we need to do is integrate, we're pretty much stuck. But remember, we know that this thing has a unique solution, so we're just after a single solution. So maybe the single solution comes from these moments where we did this division. Notice that if we were to check these as potentials for yielding a solution, and if we were to go look at this, well, y squared not equal to 0, I mean, that would imply just y is 0, and actually, arctangent of y being 0, that's the same, right? The only time arctangent is 0 is at 0. So arctangent of y equals 0 also implies y equals 0. So let's check y equals 0. Well, if we check y equals 0 in the differential equation, the left-hand side obviously is going to be 0 because the derivative of 0 is 0. And the right-hand side, well, forget about all that, so just look right there. 0 squared is going to be 0. That entire thing is going to be 0. So it works. So y equals 0 solves the differential equation. But we're trying to solve the IVP. Does y equals 0 satisfy this initial condition? Well, it does, because at x equals 0, what is y? 0, because for any x, y equals 0. So y equals 0 satisfies y of 0 equals 0. It would satisfy it even if it was like y of 10 equals 0, because y equals 0 is always 0. It wouldn't satisfy it if the initial condition was like y of 0 equals 1, because then we would need y to be 1, and y equals 0 is never 1. But in this case, it does solve the differential equation. It does satisfy the initial condition. We know from our work up here that it has a unique solution, so that's got to be it. So the unique solution here is y equals 0. Now, the reason I wanted to do this example, partially is, again, just to review a little bit about the existence and uniqueness theorem, and partially also because I want you guys to sort of see in an actual example. I mean, this is just sort of a funny one with the arctangent and the y squared and the e to the x squared and all that craziness. But what's sort of unique about this is the power that you get from knowing that an IVP has a unique solution. We don't have to worry about doing all this messy work that actually is impossible to come up with a closed form for, because we know there's only one single solution, and we're able to find that one single solution very easily. So this basically sort of shows you guys why it's so important to understand when we have unique solutions, or if you're ever told that something has a unique solution, why that's such an important piece of information. All right. We're ready to wrap up this video by talking just briefly about some different examples. We've made a lot of mention about different sorts of solution sets, so I want to make sure you guys see some examples to really understand what are the possibilities for the solution set of a differential equation. So this is just some commentary on solution sets to differential equations. We're not going to work through these really, but I just want you guys to sort of see that each of these situations are possible. So first, there are differential equations out there with no solutions. Definitely happens. We're focusing on the class on solving differential equations, so we focus on the ones that have solutions. But there are certainly, just like algebraic equations that don't have solutions, differential equations don't have to have solutions. Here's an example. It's sort of dumb. It says y prime squared is negative 1. Well, as we know, if we're working over the real numbers, it's impossible to square a number, let alone a function, and get a negative number. So we know that there would be no solutions for this. Could we come up with less sort of dumb examples? Sure, but we just wanted to see one to really show you guys that it is possible for a differential equation to have no solutions. It's possible for differential equations to have a finite number of solutions. This differential equation, this here, y times y prime squared equals negative y. If you think about this, if you were trying to solve this, the first step you would do is you would divide by y, and you would get y squared equals negative 1. So you might say, well, that means there's no solutions. But the step to go from here to here was under that assumption that y is not equal to 0. If we actually check that off to the side, check y equals 0. So if you check y equals 0, plug it in on the left-hand side. Well, y is going to be 0, y prime is going to be 0, this is all going to be 0. Negative 0 is 0, so left-hand side 0, right-hand side 0. Check, right? So this would tell us that y equals 0 is the only solution, right? Because we know there's no solutions to this, but this guy actually does have the solution y equals 0. This also tells you guys that when you do an operation like dividing by the function of the dependent variable, you're really changing the differential equation. This differential equation here and this one here are very related, because if you make that operation of dividing both sides by y, you get the same thing. But the difference is this one started like that, so this one has no solutions. This one up here has no solutions, whereas this one, because it started from here, has y equals 0 as a solution. Is it possible to have any finite number of solutions? Yeah, you could just keep stacking onto this. If we wanted 2 solutions, we could do the example y minus 1, y prime squared equals negative y minus 1, y. And then you would divide by y minus 1 and y. And then you'd have the solutions y equals 0, y equals 1, but that's it. So when we say finite number, we mean any finite number. There are differential equations out there with 1 solution, 2 solutions, 17 solutions, whatever. Any finite number, you can find a differential equation that has that many solutions. All right, these are definitely weird cases. A lot of the ones that we've been doing have infinite solutions. So there are differential equations with an infinite number of solutions, where these solutions can be expressed as a general solution. This is the situation that we're always hoping for. We really like when things have a general solution. Here's a very basic example, y prime equals 1. This is actually technically separable. You can think about it as y times 1 times y prime equals 1. And if you integrate both sides, well, you would get y equals x plus c. So this has an infinite number of solutions, right? You've got solutions like y equals x plus 1. You've got y equals x minus 3 halves. You have y equals x plus pi. Any of those are all solutions. So it has an infinite number of solutions. But they all have a single form, so this is a general solution. So this is an example of a differential equation with a general solution. These are the ones we really, really hope for. This is sort of the nicest thing that can happen with a solution set for a differential equation. Then, as we've run into, there are some differential equations with an infinite number of solutions where unfortunately the solutions cannot be expressed as a general solution. Very similar to this one, we have y prime equals y. If you think about this, you could start by dividing by y. You get y prime equals 1. We know that that then has the solutions, y equals x plus c. So that guarantees that it has an infinite number of solutions. But, of course, the step we took to go from here to here was under the assumption that y is not equal to 0. If you check that off to the side, we can sort of check y equals 0. On the left-hand side, it's going to be 0. On the right-hand side, it's also going to be 0. So left-hand side, 0. Right-hand side, 0. Check. Well, that means it works on both sides. That means it is a solution. So this solution set then here would be y equals x plus c. That's an infinite number of things, as well as this one extra one, y equals 0. Maybe y equals 0 lives inside of here, but of course, everything in here is of the form y equals x plus some number. There's no choice of this number, which would then make this thing y equals 0. You might say, why don't we choose c to be equal to negative x? Well, remember what c is. C is a constant. You can let it be any constant you want, but it cannot be the independent variable. It's just a single number. So this would be a differential equation that has an infinite number of solutions here, but also has this solution there, so it cannot be expressed as a general solution. So when we're talking about solution sets for differential equations, all these things are possible options. No solutions, finite solutions, infinite solutions that are in a general format, infinite solutions that are not in a general format. So this was just a brief discussion. This didn't have anything to directly do with separable differential equations, but since you guys have separable differential equations as a technique now, we were actually able to see like why this guy has this solution, because again, to actually go from here to here, you're really integrating 1 dy equals the integral of 1 dx. So you basically had to save this discussion until now, since you actually know how to solve some things now. So just wanted to make sure that we're sort of all good with the terminology about the solution sets of these differential equations. In the next video, we're going to take just a quick detour away from learning new techniques for solving first-order differential equations and talk a little bit about some modeling that we can do using differential equations.